Hi, my name is Kambiz Azarian, and in this talk, I will compare two approaches for domain adaptation of human segmentation. These are test time adaptation and training time generalization. This is a joint work with Debasmit, Hyojin Park, and Fatih Porikli from Qualcomm AI Research. The traditional approach for adapting segmentation models has been to use high confidence pixels as pseudo labels, and the problem is label noise. As shown in the top plot, setting the minimum confidence to a large value makes labels less effective by excluding part of the body, whereas lowering it induces noise by including part of the guitar. The reason is unreliability of pixel classification. Hence, one solution is to use a higher level attribute such as human keypoints, as shown in the bottom image. Given this insight, one can take either of two approaches, test time adaptation or TTA versus training time generalization or TTG. In TTA, we assume availability of a test image and allow for test time backpropagation. First, high confidence pixels are converted to pseudo labels and then backpropagated to update a common backbone which adapts the segmentation path. In TTG, we do not assume availability of any test images or change network weight. Instead, we concatenate the backbone's features with those of the keypoint head and use it for segmentation. TTA has two challenges, dependence on heuristics and pseudo-label noise. As for heuristics, note that adapting the top left image with the correct elbow position degrades the mask around the bouquet of flowers due to elbow's occlusion. As for label noise, note that some of the mask RCNN's keypoint estimates in the bottom image are quite off. We studied three keypoint head variants in addition to mask RCNN's baseline. All variants include visible versus occluded flags, and some are transformer-based. The top left table compares TTA and TTG for the ResNet50 backbone and shows that in the absence of a large domain shift, TTA degrades performance as it changes already optimal weights using few unlabeled data samples. TTG improves a little as it uses keypoint ground truth for segmentation. With a large domain shift, however, both TTA and TTG provide gains, but TTG gains are larger and less sensitive to architectural variations. The top right table shows similar trends for the ResNet 101 backbone. The bottom table shows TTG's competitivity against methods from the literature despite its simplicity. Here we give ablation results with respect to various TTA hyperparameters such as adaptation learning rate, full versus partial backbone adaptation, and various pseudo-label thresholds. We note that setting TTA hyperparameters in the absence of prior knowledge about the target domain, which is a reasonable assumption, is challenging. Per image, setting of TTA hyperparameters is even more difficult. Our conclusion is that for human segmentation, TTG gives larger gains and is more robust to architectural variations compared to TTA. TTA is heuristics dependent as pseudo-labels carry less information compared to TTG's auxiliary features. TTA further involves judgment calls when setting hyperparameters such as adaptation learning rate in the absence of prior knowledge about the target domain. TTA additionally requires test time backpropagation, which is a major hardware-software capability. Thank you for your attention.